This is the third video in the series on virtual sensors. In this episode, we'll look at exhaust manifold temperature, which may also be called simply exhaust temperature, turbocharger turbine intake temperature, or something similar to that. Some diesel engines may have a physical or a real exhaust temperature sensor, while other engines may only have a virtual exhaust temperature sensor. If the engine does have a real exhaust temperature sensor, the ECM may still calculate an estimate, which will act as a backup value of exhaust temperature if the real sensor value is determined to be by the ECM to be invalid, such as the case of a disconnected exhaust temp sensor. Monitoring the exhaust temperature is important for diesel engine reliability since high exhaust temperature can damage the turbocharger turbine and other exhaust system components. And most ECMs will throw a DTC and probably a D rate if the exhaust temperature is determined to be too high. The ECM calculates an estimation for exhaust temperature using a math and physics-based model. As for the actual math performed in the math model, it may be somewhat complicated. So instead of showing a lot of math that most engineers have never used since their last college final exam, I'll just show blocks that illustrate the general process. So reviewing the mass airflow model, which we looked at in the other episodes, the real sensor inputs I'm going to use in these videos will be shown as green blocks. We can see that engine speed, manifold absolute pressure, and manifold air temperature are real sensor inputs into the mass airflow math model. The empirical data or the other information in these episodes I'll show as gray blocks like this. In this case, the volumetric efficiency is empirical data, and that comes from or it is in lookup tables that are contained or programmed into the ECM. So the mass airflow has units of mass or weight of air per unit of time, such as pounds per minute or the metric equivalent. So although most of the information that the ECM uses to calculate mass airflow comes from real sensors, mass airflow is really an estimated quantity unless the engine has a real mass airflow sensor, since all we really know is the temperature and the pressure of the air in the intake manifold and the engine speed. The ECM really doesn't know that the flow rate, what that flow rate of air is, and if there's a problem such as an exhaust restriction or we have an intake valve that isn't opening, that's going to cause the mass airflow estimate to be either over-predicted or under-predicted. In other words, it's going to be wrong. For these videos, the estimates or calculated values are going to be shown as these yellow boxes. So like any other estimate or calculation, the information may not be correct if there are substantial errors in the input data. From computer science, the phrase garbage in, garbage out, or GIGO pretty much describes any math model or any attempt at estimating. If the faulty measurement is used as an input for some estimate, that error is going to carry over into all downstream estimates, and as we'll see later, that may even be amplified. So looking again at this engine model, I've added a high-pressure common rail fuel system, along with a fuel rail pressure sensor and a fuel temperature sensor. The ECM on engines with other types of fuel systems, such as a unit injector fuel system, we can also estimate the exhaust manifold temperature, but with less accuracy since the injection pressures can't be directly measured like they can with a high pressure common rail system. Also, to simplify these videos, EGR is going to be ignored for now since it does somewhat complicate the exhaust temperature model. The other primary or main input to the exhaust temperature math model is the mass or weight of the fuel that is injected. The ECM must calculate the mass of fuel for each cylinder firing event, which is typically measured in units of milligrams per stroke. The ECM determines the mass of fuel to be injected to reach or to maintain the desired engine speed or governor reference speed. The ECM does not directly measure the mass of injected fuel, but rather calculates it based on sensor inputs and empirical data. The ECM calculates the mass of injected fuel using fuel rail pressure, fuel temperature, the commanded injector on time, and empirical data regarding the specific injectors that are used. This empirical data includes the flow characteristics for that particular injector part number, which is provided by the injector manufacturer. And then this is stored in the ECM as a lookup table. The IQA injector quantity adjustment strings, those things that you have to change when you change an injector on some engines, may also be used to fine-tune the injector flow rate for each specific serial numbered injector to take out manufacturing tolerances in the injectors. Engine speed and constants such as the number of cylinders are used in the math model to convert the individual mass of fuel per injection event, such as milligrams per stroke, to what we'll call a mass fuel injected, the mass of the fuel injected, which we'll use in this case pounds per minute, just like the air flow. We can also use the metric equivalent, of course. Because the ECM really doesn't know if the calculated mass of fuel has actually been injected when commanded, the mass fuel flow is really estimate like mass airflow. Therefore, fuel mass is going to be shown as a yellow box because it is an estimate. The fuel injectors themselves are a potential source of uncertainty in this calculation. So the quantity of fuel that is actually injected heavily depends on the flow characteristics and the electromechanical actions, the hydraulic actions of the injector, which may change over time due to wear or damage. The ECM may be able to monitor if we have a drop in rail pressure when an injector is commanded on to determine that it actually injected some fuel, but accurately determining or verifying the mass of fuel injected based on rail pressure drop isn't probably possible. And as we'll see later, injector issues can surely be a source of exhaust temperature diagnostic trouble codes or problems, as we'll show later on. So the mass airflow rate and mass of fuel injected rate are inputs to the air to fuel ratio calculation. Because the mass airflow and the mass of the fuel injected are estimates, the air fuel ratio is also an estimate. There's no real or physical sensor on the engine which measures the air to fuel ratio on most engines, although some engines may have a wideband O2 sensor which can be used for that purpose. You've probably heard of stoichiometry and probably know that for gasoline spark ignition engines, the theoretical stoichiometric air to fuel ratio is about 14.7 to 1 by mass. This means that 1 pound of gasoline will require 14.7 pounds of air to fully combust. In diesel engines, the stoichiometric air-fuel ratio is about 14.5 to 1 by mass, so it's very close to gasoline. However, you would seldom see in a modern diesel engine being operated at this rich of an air-fuel ratio. Instead, the air-fuel ratio under load for a diesel engine may be 20 to 1 or even more. Diesel engine air-fuel ratio at low loads may be 40 to 1 or higher. Obviously, if this were a spark ignition gasoline engine, it would lean misfire at these high air-to-fuel ratios. It's probably worth mentioning one of the big differences between gasoline and diesel when it comes to air-fuel ratio. A lean mixture of, we'll say, 17 to 1 in a gasoline engine under load, if it didn't misfire, may result in burned valves and holes burned through pistons and other damage. Whereas that same 17 to 1 air to fuel ratio in a diesel engine may actually be too rich for a lot of operating conditions, even though both fuels have nearly the same theoretical stoichiometric ratio of about somewhere around 14.5 to 1. The diesel fuel has about the same energy by mass or weight as gasoline, but diesel fuel burns at a much slower rate because it's less volatile or evaporative than gasoline. So if I added excess air above stoichiometry to a gasoline engine, that's like cranking up the oxygen on an acetylene torch, and it results in a higher temperature flame, as you know. However, if I add excess air above stoichiometry to a diesel engine, what it does is it increases the probability that each of the hydrocarbon molecules of this slow-burning diesel fuel are going to have time or the opportunity to be able to find oxygen in the air to complete combustion. There's not sufficient oxygen for all the diesel fuel to complete combustion. The remaining fuel may continue to burn late into the power stroke or even after the power stroke, resulting in increased exhaust manifold temperatures. Even though a 14.5 to 1 diesel air fuel ratio is in theory stoichiometric, because of the relatively slow burn rate of diesel fuel, there's not sufficient time for all the fuel to find oxygen to combust during the power stroke, especially as the engine speed increases. So air-to-fuel ratio is one of the main inputs to the exhaust temperature estimate. As the air-fuel ratio decreases or becomes richer, the exhaust temperature increases because in part due to that slow burn rate of diesel fuel. Conversely, as the air-fuel ratio increases or becomes leaner, the exhaust temperature in general decreases. Therefore, exhaust temperature is said to be inversely proportional to air-to-fuel ratio. Some additional information is required for the UCM to accurately calculate exhaust temperature besides the air-fuel ratio. The value of engine speed, manifold absolute pressure, manifold air temperature, and fuel rail pressure are typically direct inputs to the exhaust temperature math model, as well as being inputs to the air-to-fuel ratio. So looking at MAP, as MAP increases, assuming we have no other changes, the direct MAP input to the exhaust temperature model causes the calculated exhaust temperature to also increase. So we're going to say, or we're going to indicate that exhaust temperature, in this case, is directly proportional to MAP. However, as MAP increases, the mass airflow also increases, which causes the air-fuel ratio to increase. Since we said that exhaust temperature is inversely proportional to air-fuel ratio, the calculated exhaust temperature will decrease because of the increase in MAP to the air-fuel ratio. This may seem conflicting, but the final calculated exhaust temperature due to the MAP increase will cause exhaust temperature to be changed by whichever of the calculated temperature changes is greater. For example, if we have an increase in MAP that causes the calculated exhaust temperature to increase by 20 degrees due to the direct input to the math model, but also causes the calculated exhaust temperature to decrease by 5 degrees due to the air-fuel ratio increase, the overall exhaust temperature estimate will be increased by 15 degrees, for an example. Looking at manifold air temperature, as manifold air temperature increases, assuming nothing else changes, the direct manifold air temperature input to the exhaust temperature model causes the calculated exhaust temperature to also increase, indicating that exhaust temperature is directly proportional to manifold air temperature. Additionally, as the manifold air temperature increases, the mass airflow rate decreases, which causes the air-fuel ratio to also decrease. And since exhaust temperature is inversely proportional to air-fuel ratio, the calculated exhaust temperature will also increase due to the increase in manifold air temperature as it goes into the mass airflow estimate. Therefore, any increase in manifold air temperature will cause the exhaust temperature to also increase. Since manifold air temperature is being used in two places in the math model, there's a doubling effect. A small change in manifold air temperature can have a much larger impact on the calculated exhaust. Looking at rail pressure, as rail pressure increases, assuming nothing else changes, the direct rail pressure input to the exhaust temperature model causes the exhaust temperature to also increase, indicating that exhaust temperature is directly proportional to rail pressure. Additionally, as rail pressure increases, the mass of fuel injected increases, which in this case causes the air-fuel ratio to decrease. Since exhaust temperature, as we said, is inversely proportional to the air-fuel ratio, the calculated exhaust temperature will also increase due to the increase in rail pressure as it inputs to the air-fuel ratio. Therefore, like manifold air temperature, any increase in rail pressure will cause the exhaust temperature to also increase. The other input to the exhaust temperature model is injection timing. Injection timing has a direct effect on exhaust temperature. The ECM must, as we know, provide precise injection timing to fractions of a degree of crankshaft rotation based on the information or the input of the engine crank position sensor. ECM has to take all of the mechanical, electrical, magnetic field development delays of the injector. In addition to the fuel ignition delay, that time for the fuel to actually start combusting after it's been injected, has to take all that into account for optimal injection timing. Even though these time delays may all add up to less than a millisecond or two, if you get the injection timing wrong, the engine performance and the exhaust emissions are really going to suffer. The good thing, though, as technicians, is that a problem with the crank position sensor is going to it may cause a problem with engine speed measurement as well as crankshaft position. Hopefully these are rare. These types of failures are rare since they're probably going to cause the engine to not run at all or to run very poorly. Ideally, we'll get a DTC that'll indicate that we have a problem with the crankshaft or the camshaft position sensor. In closing, this may seem like a lot of information, but the key takeaway is knowing what real sensors and empirical data go into this exhaust temperature calculation and the direction that they may cause the estimation to go if there's a measurement error or something else wrong with the engine. In the next video, we're going to look at how to diagnose some of these high exhaust temperature problems on a real engine.